this example, we are going to look at the recombination portion of a PEC made with ColRadPy. So as before, in all previous examples, we need to import NumPy and matplotlib. The next thing we're going to specify is our directory to ColRadPy, and then from ColRadPy, we're going to import ColRadPy. So as in the previous example, here's the helium-like oxygen file we're going to be using. We've got a different temperature grid and a different density grid because we're only going to plot one density. Again, here we're only saying that the ground is metastable, so that's why the metastable array is just a single zero. So again, the call to ColRadPy is the file, the metastable array, the temperature array, the density array. We're going to leave on ionization and supplementing the ionization rates with ECIP. What's different with the last example now, we are going to use the three-body recombination rates. So three-body recombination is made through a detailed ionization balance with our ionization rates. So to use recombination, three-body recombination rates, we have to have already ionization rates included. The next thing is using recombination rates that are included in the ADF04 file. So this would be dielectronic recombination and radiative recombination. Again, we are going to have SciPy1D interpolating using cubic splines for both the collisional excitation rates in the ADF04 file as well as the recombination rates in the ADF04 file. So these calls look very similar to our last example where we're going to make the excitation rates, make the ionization rates, supplement with ECIP. Now what's different here is we are going to make recombination rates from the file, so this is going to interpolate our recombination rates from the ADF04 file on our temperature grid. And the next thing that's going to happen is three-body recombination is going to be made using a detailed balance relation with our ionization rates. The next thing that's going to happen is we're going to put all of these different rates into the correct spots in the matrix, and then again we are going to solve with the quasi-static approximation. So again, this is setting up stuff for plotting, and because we're only plotting one density here, there's no for loop, and we are going to plot against the temperature grid the X and Y line, which again we know is the first PEC index, so that's how we specify it here. We're going to specify now the ground. So the way this axis works is it goes in the charge state you have specified up here, ground, and then any metastables, so it goes in the order of the metastable array. After that, it goes into the ground state and any metastable states of the next charge state up. So that's why to plot the excitation portion of the PEC, we are plotting the first one corresponding to the ground state. So this is the excitation portion. Down here, we are plotting the recombination portion. And so an index of 1 here corresponds to the ground of the hydrogen-like oxygen system that is actually doing the recombining. And so in each of these, what I'm going to do is they are going to be normalized to their max value. This is just because excitation rates and recombination rates can be pretty different, so this is just helpful for plotting. And then what's left here is just some plot decoration. And so if I run this, what we are going to see is we are going to see the PEC versus temperature from each of the excitation and recombination portion. So if you were to actually model the spectral line, what would need to be done is these PEC values would need to be multiplied by the fractional abundance of the helium-like system, which is responsible for our excitation contribution, and then the fractional abundance of the hydrogen-like oxygen, which is responsible for our recombination portion of the PEC. And so this would need to be, what would need to happen is a steady state ionization balance would need to be run for each of these temperatures, because at each of these temperatures, a different fractional abundance for helium-like to hydrogen-like exists. And so what we can see is recombination rates are very strong at low temperatures, which is generally the case, that the cross sections increase significantly with decreasing temperature. And then we can see again that the excitation rates increase with temperature.